Hello again. So, welcome to this first proper lecture of this course, Radiation Damaging Materials. So this is a course which really tries to be a contemporary course on the what's known about radiation damage in all classes of materials, with some emphasis on the theory and simulation methods used in the field. So a little bit of background for this course. This was actually first done in 2014 for a Swedish-speaking teaching at the University of Helsinki. Our university is a bilingual university, officially with Finnish and Swedish, and in practice we teach actually a lot, or maybe more than in Finnish, even in English nowadays, but we still use three languages. And this is a course at our university, but we have now also made this MOOC, massive online open course version of it, so that anybody in the world who cares can listen and do this. We have been working on this field for a long time, and that's why we think we are happy to give this course and have some expertise on the topic. Of course, we don't take any responsibility for what happens. I mean, this is giving the basic physics. Practical work, of course, also requires a lot of knowledge about how to handle materials and radioactive materials equipment safely. And this course does not really teach that. And if you do anything like that, you should make sure you have the appropriate knowledge to do things safely. A little bit about our background. So I'm the main lecturer, I'm Kai Nordlund, and I'm a professor in computational materials physics, but specializing in radiation damaging materials. And then there are two other senior scientists, Flora Drabekova and Antti Kuronen, who have contributed also to these lecture notes. And we are very grateful that Professor Bill Weber from the University of Tennessee has also looked through these notes and provided some constructive comments on them, but he certainly does not guarantee that everything is correct, and neither do we. To get towards the physics, so what's the aim of the course? Well, to understand, the basic aim is to understand what radiation damage is and how it's created, and how it can affect material properties. We won't, of course, go through all the knowledge in the field. It's a big field with vast knowledge gathered during the last 150 years or so, but we try to give the basic. And we give a little bit of basic about experimental methods, and somewhat more actually on computer simulation methods. And the computer simulation methods have the big advantage that they are very useful for the theoretical understanding of the field. So what should you know to go to this, take this course? At our department, we have courses in thermophysics or statistical physics, the structure of matter, and materials physics. And I would believe that most physics or material science course departments in the world have something similar, and we assume that people have taken these courses. So thermodynamics, basic thermodynamics, pressure, temperature, and so on. It's very important to understand that. We assume people know about crystal structures. We don't give the basics of crystal structures, but we assume that people know this. And then also about the somewhat about other phases of matter. We also assume that people know the basics of quantum mechanics, that there is the wave functions and Schrödinger equation and so on. Although to pass the course, one doesn't really need to know it, but more than on a qualitative level. So in a physics curriculum, typically I would say this course would be in the first or second years or a master of physics program. Although it might also be in some universities in the last year of a bachelor studies. So this course, it's made by us, mainly myself, gathering material also from some conference presentations and other courses to some extent. So So there is no single book which would cover the same material we have on these lecture notes. So the main material is the lecture notes. But if you want in-depth knowledge and especially more thorough description of the equations of binary collisions and many other things, we can warmly recommend this book by Gary Wass on fundamentals of radiation materials science, which is quite an extensive book with lots of details and also lots of stuff which is not covered in these lecture notes. But we don't require anybody to purchase this book. Also, there is plenty of material in the web, and this is just some review articles we have partly been using also to make these lecture notes. As you see, the last three are from our group, but the first one is a bit older, but a very good basic introduction to this. And there are many others, and also on the course web page we give some, and in the lecture notes we try immediately when we pass the very basic knowledge, we try to give references to all the materials, so you can check the scientific references. Almost all of them are available in the web, either for free or at least via university library. So, okay, and now getting closer and closer to the actual physics. So, first of all, in the course names, there is the name radiation. So, to understand what radiation damage is, you need to know what we mean by radiation. And this is actually a little bit complicated because this word radiation linguistically is used in the somewhat different meanings. And this is true actually in all of the languages we know. So first of all, if you have taken an electrodynamics course, you know that solving the Maxwell equations for a moving charged particles induces an electromagnetic field, but not energy transport. But if you have an accelerated particle, that is, you have a particle which is not just moving, but moving faster, then it will always lead to radiation, that is electromagnetic radiation, which is emitted outwards from the system and also carrying energy with it. And in almost all cases, this is in the form of radio waves. And this is often called radiation, but this is not radiation in the sense what we mean in this course. Because what we talk about in this course, we talk about higher energies than radio waves, which come from, for instance, radioactive decay, suns, the stars, and so on. But then the other cases, again, in contemporary talks, as if you talk about the headlights of a car, that's not ionizing radiation, that's regular radiation again. So for the purpose of this course, we really talk about what is ionizing radiation. That is the kind of radiation that can cause damage to materials or living beings, biological materials, and this is what the word ionizing means. And we'll give a little bit more details in a couple of slides. The thing about this ionizing radiation, it's also a legal term, that is the radiation protection legislation in probably all countries uses this term ionizing radiation. Okay, so you have to be a bit careful about terminology. This is the basic message here. That is, we physicists, again, when we talk about radiation, we quite often mean ionizing radiation. And this actually language, it really exists in all languages. I gave the Finnish and Swedish translation earlier on. Germany has the German and Russian language have the same issue. So, but we are now interested in ionizing radiation. And from a physics point of view, one can put a fairly well-defined limit of what's ionizing radiation. And this comes from the strength of chemical bonds. Chemical bonds have strengths of the order of 2 to 5 eV, and because of that, ionizing radiation can be defined as radiation from particles that have an energy high enough to break these chemical bonds. Because if you break chemical bonds, then rather obviously you start damaging the material. So roughly speaking, one could say that particles with an energy of 5 eV or higher may be ionizing. But this is not an exact limit. And during the course we will see somewhat later examples of what the more precise mechanism of causing damage is. But one important thing to know that laser irradiation, if you have lasers in the visible range, the photon energies are clearly less than 5 eV, and it's not ionizing, even though if its intensity is high enough, it can damage material. Sorry. Yeah. And this term ionizing radiation is actually defined as I said, in most laws, and here is the Finnish law, how it is defined. This is an English translation of the Finnish law, and here actually nicely enough, when the law was made, it was defined that what radiation is, that it includes is ionizing and non-ionizing radiation, then ionizing radiation, and then given what it is. According to here, it says that ultraviolet radiation is non-ionizing, and from a physics point of view, this is slightly problematic, because the higher energy UV radiation can break chemical bonds and can, of course, as you probably well know, can even cause skin cancer and so on. So the legal definition is slightly problematic as well. Okay, so now we continue. Technically, there was a small break in the recording, so that there may be a slight shift in now in the video. But yeah, so now we'll start getting slowly deeper into the physics of what's going on. So we have defined that there is ionizing radiation, but the next obvious and big question is what can cause ionizing radiation? Well, in physics we know that due to the particle-wave duality, everything is either a particle or a wave, but at high energies most quantum waves behave like particles. So for practical purposes, we can pretty much talk about energetic particles when we talk about causes of ionizing radiation. And for this, we have the first kind of particles we consider are photons, which are of course a very, very important part of all of physics. And the photons' electromagnetic radiation has a very wide range of energies encompassing something like 20 orders of magnitude or wavelength or frequency. And all of these are interesting in physics. But now, for the purpose of this course, what's most interesting is X-rays and gamma rays, because they are clearly ionizing radiation. And as mentioned earlier, ultraviolet can also be ionizing radiation. So all of these are of interest of this course. And here, this graph is a little bit simplified because in reality, X-ray and gamma ray energy actually overlaps. And also the synchrotron radiation coming from synchrotron particle accelerators is pretty much the same as X-ray photons. But for this course, it's not actually so significant what the source of the radiation is, as long as it's in this high energy range where the energies are above an electrovolt or so, a few electrovolts or so. Well, before we go on, one maybe should make the comment that currently in 2020 there is a ongoing debate of whether 5G and other radiation from mobile phones can be harmful to humans. For For this course, we don't have to answer the question, but we can make the point that note that radio waves and microwaves are way below in energy compared to the actual ionizing radiation here at the high energies. One can make a simple calculation. For 5G mobile networks, the maximum frequency that maybe might be used is something of the order of 100 gigahertz. Most of the time, the 5G networks work at much lower frequencies. But even if we take the maximum frequency, we find that the energy of photons with this frequency is only 0.4 milli electrovolts. And this is 4 orders of magnitude below those energies needed to break chemical bonds. Hence, it's pretty clear that 5G photons cannot possibly break chemical bonds directly, and they cannot cause biological damage in the same way as the ionizing radiation. So this standard mechanism of radiation damage definitely do not apply to mobile phones. And if there is a damage mechanism, there is no good understanding of what that damage mechanism would be. We do, of course, know that if you have a high enough frequency, high enough intensity, high enough microwave intensity, you can heat up stuff. This is the way a microwave oven works. But the mobile phone, of course, intensity should not be so high as to cause a significant heating of biological tissue. So it's that cannot at least directly be the possible reason to damage from mobile phones. But for the rest of the course, we won't discuss this issue at all. We will discuss the known or somewhat known mechanism of radiation damage from ionizing radiation. Well, going on with possible particles, then we of course have electrons, which are also a key particle in physics. And the electrons can be accelerated. They are charged particles, so they are easy to accelerate. And if they are accelerated to high energies, one can certainly cause radiation damage from them. And there are many ways to accelerate them. The most wide outspread is the old-fashioned TV. The old-fashioned cathode ray tube TVs worked with an electron accelerator, which typically had a voltage of 25 kilovolts. So this is energy enough to accelerate electrons to 25 keV, which is in the ionizing damage range. The reasons TVs weren't horribly dangerous because they had a screen and the accelerator electrons were stopping in the fluorescent screen and they didn't penetrate the screen for sure. However, they did produce, especially in the old ones, a little bit of X-rays when they hit the screen. And so in principle, one could get a little bit of a ionizing radiation dose from old-fashioned TVs. And the older one of us remember that there were warnings that one should not sit too close to a TV screen. The modern flat panel these days do not have this issue, so now by now this issue is moot, unless you somehow still happen to find a cathode ray tube TV and watch it. Well, going on, we have neutrons. Neutrons is not a stable elementary particle, but it does exist for 11 minutes, which is easily enough to hit a lot of stuff if you have a neutron traveling. And so it is possible to get free neutrons. They come naturally from natural radioactive decay. Each one of us, every room, every building has a very small fraction of radioactive isotopes which produce neutrons, so there are neutrons all around us. And then it's possible to produce neutrons in high amounts in nuclear fission and nuclear fusion reactors. Usually they are produced at high energies, mega electrovolt energies, then they are thermalized to lower energies for a sufficient absorption in efficient nuclear reactors. Later on during the course, we will talk to a fair amount about how neutrons can cause radiation damage. This is one of the biggest fields of radiation damage is certainly neutron damage in fission nuclear reactors. For neutrons, there is a classification of their energy. I won't read this out aloud, but you can see that there is a classification how different energy neutrons of different energies are called different things. And for radiation damage, most of the concerns are about the fast and very fast neutrons with keV or MeV energies. And the fourth main category is ions, that is atoms or molecules which are ionized so that they have an electric charge and then they can be accelerated. And this brings us to the range of accelerators, particle accelerators, which exist at CERN, but also exist in many other places. The minimum ion energies for accelerators are the order of 10 electrovolts. The highest ones are of the order of 7 tera electrovolts. So there is a very wide range of energies which can be particles which can be accelerated by accelerators. And we will return also to this issue, but I already now note that accelerator technologies are actually a real industry because they are used in manufacturing computer chips, including the chips on the computer or mobile phone you are working on right now. And ions can also be produced naturally by radioactivity decay, and in the solar system the sun produces a lot of energetic ions. It's mainly protons in a wide energy range. Well, this is not the full list. There are other cases of particles which can be ionizing. Neutral atoms can be high energetic, although it's very difficult to make them so because typically accelerators deal with the ions. Sometimes they are neutralized, and plasmas they are neutralized spontaneously, and so on. Plasmas produced a lot of both ionized and neutral energetic particles. But then any elementary particle can, at least in principle, have a high energy and can be a source of damage. And in high energy particle accelerators, the muons, the antiprotons, the positrons all can produce some damage in the components there. Solar neutrinos can hit with a very low probability, can hit atoms and can cause damage and so on. And so there is a wide range of these. Out of all these, the one very important one which also exists in nature is the cosmic muons. These are muons and elementary particles which are formed when mainly when the solar wind hits the upper parts of the atmospheres. Some nuclear reaction causes cosmic muons, and these go through us all the time. We are all the time bombarded by cosmic muons, and this can be also damage sensitive modern electronics. And there is dark matter may exist, and if it exists, it may cause actually radiation damaging materials, although this is very speculative. There is no experimental proof of it, but several theoretical papers working on this. Then I already mentioned that molecules can be ions, can be accelerated, nanoclusters can be ionized, can be accelerated, so also bigger particles can be causing the damage. Well, and so this is sort of a brief introduction to these topics. So this course and study of radiation damage, it's linked to nuclear physics, but it's not entirely part of it, because nuclear physics studies the atomic nuclei, nuclear reactions, what the properties of nuclei, what happens inside them, whereas radiation damage is mainly composed of what happens to materials. So at least I personally would call radiation damage studies a branch of materials physics. Some people talk about radiation materials science, which is actually a pretty nice term. It's a new science which is more on the material side, although of course linked to nuclear physics. And at the end of this introductory section, still mention one thing which is very important to know for practical purposes, although it doesn't teach any new physics, is that historically people have been also talking about alpha, beta, gamma, delta radiation. And these names, which just come from the Greek letters in the sequence they start, they of course were given when it was not fully understood what they were. Nowadays, we know that alpha particles are just helium nuclei, ionized helium nuclei with 2 protons and 2 electrons. Beta particles are free electrons when they have a high energy. Gamma rays are the high energy photons. And finally, delta electrons. This term is not used so much more, but it is still used in some branches of radiation materials science. This means secondary electrons, which are produced when another energetic particle interacts with matter. So it is important to know all of these for the purposes of this course. And now I'll still make the connection to radiation protection terminology. This course is not about radiation protection. Most probably all universities have separate courses on radiation protection, but because the things are of course somewhat related here, we'll make this connection, but then not really talk much about it for the rest of the course. So, but first let's start with some very basic terminology. So we are talking about radiation damage, which means that the material is modified by radiation and which causes damage. It's not necessarily harmful. The word damage is a bit misleading, with that sometimes radiation damage is extremely useful, but it's still called damage. Then defects are in general called atoms that deviate from the regular equilibrium order in a crystal or amorphous material. And defects can also be produced by completely other stuff than radiation damage. But often they are the end result of radiation damage is almost always some sort of defect, so these terms are again interlinked. And we will go a lot more detail about defects in this course, especially sections 6 and 9. But there are other kinds of radiation damage than defects. One can amorphize a material into a stable or metastable phase. This is not really a defect, it's a different phase, but it's an effect of radiation. And as I said already, they can be beneficial, so their damage is by no means always harmful. But then we go on to the radiation protection, kind of more to the that kind of terminology. So one can talk about exposure, which means that you expose a material to irradiation. Then how much exposure has happened or how fast it happens can be defined with these 4 quantities. And it's important to remember which one is which. So dose is defined in units of energy. Dose rate is dose over time, so this is simple. Then fluence is defined as particles over area, or sometimes particle over volume, but it doesn't have energy units. So this is the big difference, that the dose has energy units, fluence does not. Then there is flux, which is fluence over time. So this is, once you know what fluence is, flux is very simple. And then there is the term activity, which means how much radiation is produced by a radioactive sample. And here is some units for these. So dose, as I said, is important to remember. It's in units of energy. And it has an SI unit of Gray, which is joules of radiation per kilogram of material. It also has many historical units, which are still used to a fairly large extent. In physics research and in this course, we use a lot the unit electrovolts per atom or electrovolts per cubic angstrom or maybe cubic nanometer, which is dealing on the atomic level. Of course, we like to use electrovolts unit. Then there is a very special unit called displacements per atom, which is essentially a dose unit, although formally it's unitless. And this we will return to in sections 4 and 5, what this displacement per atom unit actually is. Well, dose rate is simple gray per second, fluence is simple particles per centimeter squared or particles per meter squared, then flux is the same, but also divided by time, so per second. Well, then the radiation protection units, really, which are only used in radiation protection. Radiation protection uses a lot the units of equivalent dose, and this is a dose which is used for only for living humans, which is the real or SI dose multiplied quality factor, which vaguely tells how dangerous different kinds of irradiation is. So this quality factor is 1 for 200 keV photons, 2 for protons higher than 2 MeV, 20 for MeV alphas. Neutrons have a more complex definition. This is a function of the linear energy transfer, that is how much energy loss has been deposited per length traveled, also known as the stopping power. So this is the SI unit Sievert for dose. The old unit REM, radiation equivalent man, stupid and misogynistic unit, but anyway, this is still REM is still used quite more extensively in the field. And as said, this is not a course on radiation protection, so we won't go into more detail on this, except that to show that if you're interested in what may be interesting to understand the orders of magnitude, the Wikipedia page on Sievert has a very nice chart on radiation dose, which starts from extremely more small exposures, like eating one banana, which actually does give you radiation, because bananas contain a good deal of the element potassium, and potassium has a radioactive isotope potassium-40, which exists in bananas, so that makes bananas a radiation source. And this then shows, going from blue to green to red, how much stepwise you need to go up to get that to actually dangerous doses. So starting from sleeping next to someone, 0.05 microsievert, to being next to the Chernobyl core, you see that there is many orders of magnitude difference before you get to the really high level, dangerous levels of radiation. And as a funny illustration of this, that yeah, eating a banana gives you radiation. If you would eat 50 million bananas in about a day, you would get so much radiation that you would die from the radiation dose. Of course, you don't have to be a genius to realize that if you try to eat 50 million bananas in a day, you will get lots of other problems. So the radiation certainly wouldn't be the worst problem of them all. So this was this first section. So here we are listing what you should have learned by reading this section. I won't read them aloud. I will give you a minute to read them yourself before we finish this video. So thank you, and see you virtually in the next lecture notes.